Alrighty, guys. 101. That's a good start time, right? Thank you for coming on Friday. I was a little uncertain how you guys would feel about that, but I can see you're nothing short of enthusiastic. Let's switch over to here. I appreciate you coming on a Friday. I really do. I know that we've got these Monday holidays, and this is just a good way for me to squeeze in some extra material. I would hate for you to miss all of everything that is MR. And I like this class a lot. Maybe you can tell that already, but it is actually a challenge for me, at least, to cover the material that I think really should be covered on the quarter system. This would be great as a semester class. And as a quarter-long class, we really kind of have to pack it in. But all the same, let's get underway. So this is where we are today. We started the first lecture as building our understanding of B0, and then we sort of talked about nuclear precession and equation of motion last time. I want to introduce a new hardware component today. It's the B1 system. So we'll talk a fair bit about the hardware componentry of the B1 system. This is the principal exciting field, right? This is the B1 field you can associate or affiliate with the radio frequency field. And I want to talk about how we generate radio frequency pulses. These are electromagnetic pulses that are used for things like excitation. And probably, in some sense, one of the most important things that B1 pulses do is they help us generate transverse magnetization. And it's only transverse magnetization that our coil and receiver system is sensitive to. So it's really important that you can generate transverse magnetization because that's what we're able to actually measure and detect. There's a lot of interplay. We'll get into this when we start talking more about pulse sequences. A lot of interplay between the longitudinal and transverse magnetization that's central to image contrast, for example. But it's important to remember that we're only sensitive to detecting or measuring information that's stored in the so-called transverse magnetization. And we'll talk about that a bit today as well. So this we just looked at. This is effectively where we are in building up our understanding of the sort of chain of events required to go from magnetic dipoles eventually all the way through to forming images. As a reminder from the last lecture, this is just where we were. We took some basic understanding of physics with respect to torques and an empirical understanding of the relationship between the magnetic dipole and the spin angular momentum. This is something that's not derivable per se, but known empirically. And what we ended up doing with that was defining a system of equations for the equation of motion for that individual magnetic dipole. And then said, well, we don't really observe things at the individual magnetic dipole level. We really do this at the so-called bulk magnetization level. And so let's just add up a bunch of these and give ourselves a new equation to work with, which we call the equation of motion for the bulk magnetization. And we're going to work with this expression a couple times today because we actually use many different B fields in MR. So the only example that we looked at last time was if the B field was strictly the B0 field, which is oriented along the K direction. And today we're going to introduce the idea of looking at RF pulses, which are just different B fields. So we still need the same equation of motion, we just have a different B field, but we have to describe that mathematically before we can really work with it well. So this is what we did. We knew how the B0 field was oriented. We ended up with a system of equations that we could sort out through this determinant operator, and ultimately solved, sort of decoupled those first order differential equations, ended up with some second order differential equations that weren't coupled, and they could get these nice looking sort of sine and cosine solutions to the behavior of the bulk magnetization components in the presence of just the B0 field. And it turns out there's a lot of different sort of ways we can, different B fields that we can use and observe how they act on the bulk magnetization. Today we're going to talk about the radio frequency B field and how it affects the bulk magnetization. We're actually going to get a solution that looks quite a bit like this, and so we'll be borrowing from the things that we saw in the previous lecture and sort of build upon those for looking at the B1 field specifically. Just a little bit about class business. Oftentimes there's some good questions at the end of class, and I want to try to address those for the whole class when I can. I won't spend a lot of time on this, but I will provide some sort of answers here. One of the questions that we had was, I brought it up sort of in writing, but we didn't talk about it a lot, was a negative sign that shows up in this sort of full form of the Larmor equation, or the vector expression of the Larmor equation. And what this really boils down to is that we know observably that the bulk magnetization precesses in a left-handed manner for a positive B field. And as such, we need a minus sign to be sort of physically consistent. I guess you could have defined the gyromagnetic ratio the other way and not had a negative sign, but this is the convention that's used. And so we want to remember that in pure vector notation, there is actually a minus sign here for the full Larmor expression, if you will. If you want to try to understand this a little bit more carefully, these are some notes from some things that I'm working on, and you can work through the mathematics a little bit more carefully as to why there's actually a minus sign that's used or needed there. So I won't go through this today. I think it's pretty clearly outlined in these equations and descriptions. Okay, so what we ended with at the end of last lecture was really a kind of stable system, right? We said we have some bulk magnetization. If you remember, we just forced that magnetization to have a particular orientation and said, there's no relaxation, let's just observe what happens. And we end up getting this description of sort of a sinusoidal variation of the X magnetization, a cosinusoidal magnetization, time variation of the Y magnetization. And the Z magnetization was stable because we didn't have any relaxation terms in there. And so the question is, well, how do we actually get to a state? The picture you want to have in mind is that when the sample goes into the MR scanner, the bulk magnetization aligns with the B0 field's direction, that so-called K direction. And we don't want it to be just oriented in that particular direction. We want to be able to tip it over. We want to be able to manipulate the spin system because we have to have some transverse magnetization that we can ultimately detect and pick up with our coil. Then the question is, how do you perturb the system? How do you go from that equilibrium state of water protons inside a B0 field to generating some transverse magnetization? And so we perturb the system by generating RF pulses, and we generate so-called RF pulses with the so-called B1 field. If you look at it from a hardware perspective, this is the teardown that we've sort of seen a couple times, and we'll work towards describing all of these components mathematically as we go. But the thing we're talking about really today is the so-called body coil. It goes by different names. Some people call it the B1 coil, other people call it the body coil. It is a transmitting coil, meaning it transmits the radio frequency pulses that we need for things like excitation. It can actually be switched very, very quickly to be used as a receive coil. So you could transmit radio frequency energy and then turn it into so-called listening mode and receive energy coming back out of the object of interest. Because that coil is relatively distant from the object itself, it's not a very good receive coil. It does have some practical uses, but in principle, it can be used as a receive coil, but it's not really done very commonly that way. So again, I've said this before, but something that I want you guys to get a good sense of, both through the lectures and from the homework assignments, is sort of the magnitudes and the time scales of the magnetic fields that we use in MR, because we really span a huge time scale and length scale and B field scale, if you will, in all the different fields that we use in MR. So let's talk about the B1 field, which we use to generate the RF pulses. The B1 field is a radio frequency field, and what makes it a radio frequency field is that it has a primary frequency in this megahertz range, and megahertz energy or megahertz waveforms we think of as being in the radio frequency range, right? FM radio stations are in the megahertz range. And so we know the gyromagnetic ratio is 42.58 megahertz per Tesla. We know then that the RF frequency we need at 1.5 Tesla is going to be about 63 megahertz, for example. So we know we're working in this so-called radio frequency range, if you will. We call these RF pulses, the B1 field rather, we call it an RF pulse because these things are also very short in duration. They're typically going to be hundreds of microseconds, maybe up to a few milliseconds long. And so again, if you think in terms of time scales, the B0 field is always on, so it has a time scale that's very, very long, if you will. These pulses are turned on for very short periods of time. And then you'll find that gradients lie somewhere in between both of these fields. We can think about the amplitude of these fields as well. We'll do a little bit of math and work out why it is that, what kind of amplitude do you need to manipulate the spins in a particular way. But, in rough numbers, the systems that we have are only capable of generating about 30 microtesla. So this is 6 orders of magnitude lower than the B0 field. So these are pretty small magnetic fields, if you will. As we work through understanding the hardware and see the mathematics, we'll see that this is actually what we call a circularly polarized field. And that means that it is a radio frequency field, but it's generated in such a way that it's actually a rotating magnetic field. It's rotating with respect to, say, the laboratory system. And it rotates at a particular frequency, the Larmor frequency, such that it's matched to the resonance frequency of, say, protons, for example, at 1.5 Tesla. It has to be rotated at a different frequency for a 3T system, and it has to rotate at a different frequency if we're trying to excite carbon-13 or 31P or something like that. These are, of course, magnetic fields as well, and so no surprise there, but we'll see how these magnetic fields specifically exert torques on magnetic dipoles, for example. And importantly, and we'll see this mathematically today, the B1 field is perpendicular to B0. So while the B0 field points along K, the B1 field is going to point somewhere in the IJ plane, the XY plane. This is just an example of sort of a typical RF bird cage coil design. What's shown on the right-hand side here is the actual copper, the rungs and the end plate that wraps around it. There's some capacitors in here as well. We'll see this in just a second. To give you a sense of scale, the patient slides inside of this. You can see some rails here, which is where the table actually slides along. And so the diameter of this is on the order of 50 or 60 centimeters or something like that. And it's the hardware component that ends up being, in terms of the sort of the MRI scanner, it's the hardware component that's closest to the patient. We'll usually have coils as well, receive coils. They're a head coil, a knee coil, things like that. So that'll be even closer to the anatomy of interest. But with regards to the sort of concentric ring that makes up the whole scanner, this hardware component is closest to the patient, if you will. This particular design is widely used. It's probably used in all modern MR systems. It's very efficient, meaning that almost all the fields, all the magnetic fields that it produces go directly to helping with imaging. There's not a lot of stray or extra fields. And that's important because you don't want to generate extra magnetic radio frequency energy that would otherwise be heating the patient. You want to use these fields as efficiently as possible for imaging only. There are still consequences of patient heating, but you of course want to minimize those as much as you can. I'll talk about some examples of this in just a second, but the field that we generate is very, very uniform, and we obviously care about that. We want our B0 field to be accurate to parts per million. Ideally, we want our B1 field to be highly accurate as well. And this particular hardware design, the birdcage coil design, gives us very uniform B1 fields radially. And that's important because we want the B1 field to act on all spins in the same way, right? We don't want it to be tipping some spins by 90 degrees and tipping other spins by 10 degrees or something like that. It does decay axially, meaning sort of along the Z direction, but that's okay because we're usually imaging near isocenter and within maybe several centimeters of isocenter. So the fact that it falls off in the, call it head-foot direction, is not a big deal. And perhaps more importantly, it's pretty uniform over a radius or over a sphere if the length is about equal to the diameter. And so these things are, of course, designed with that specification in mind. And I'll show you in just a couple slides how this is actually used to generate what's called a quadrature field, or to me, a little more logically, to generate those so-called circularly polarized fields. This is just an example of what can happen when your B1 field is inhomogeneous. So picture for now, what we prefer, say, is to excite all of our spins uniformly, right? We want to generate the same amount of transverse magnetization so that both of these locations are generating the same amount of transverse magnetization signal. If on the other hand, my B1 field is such that I tip this one all the way over, but I only partly tip this one because there's a big spatial variation in my B1 field, that's a bad thing. And so what's being shown here is that as a consequence of B1 inhomogeneity, some poor design of, or sort of poor use of the system that's in place, you can end up getting dark spots, for example. And MR can be tricky. It's very difficult to sort of identify or reverse engineer why a particular artifact exists. What's the underlying mechanism or cause for that artifact? This is a paper that was about artifacts at 3T imaging, so we know specifically this is a B1 inhomogeneity artifact, and they made some tweaks on the system, and they can flatten that out so that they get a much more uniform image intensity. But what we mean, importantly, by B1 inhomogeneity is how uniform is, say, the flip angle across the slice. And we want the flip angle to be very uniform across the slice so that all spins are seeing, say, the exact same flip angle, ideally. This is just an example of excitation in the laboratory frame. And one of the things that we're going to talk about a fair bit today, I've taken one of my favorite derivations, which is also long. I've taken it out of this lecture, and I'll get that material to you a different way, or we'll get it out of the book. That derivation is important because it helps us transform mathematically from the so-called laboratory frame to the rotating frame. In the lab frame, which is what this movie is going to show you in just a second, again, we're just standing next to the scanner and we're observing what happens to the bulk magnetization during an excitation pulse. And so the path that the magnetization carves out is sort of this spiral. And as it's spiraling, the spiraling is the precessional behavior. And as it's falling into the transverse plane, the red and green axes represent the X and Y plane, it's slowly tipping down into that plane. So some of you know a little bit about MR already. What's the flip angle for the pulse that I just showed you? It's a 90, right? So we just took the bulk magnetization, tipped it in the transverse plane. And in the lab frame, it spirals around like this. We'll see the equations that give rise to this in just a second. It ends up being kind of a pain to keep track of things in the laboratory frame. So one of the things we'll do today is move over to the rotating frame. And once we've explained and sort of talked about the rotating frame, we're going to stay in the rotating frame, I think, for the rest of the course, so to speak. So today is when we all hop on the merry-go-round, and then we're all spinning together. We'll leave it at that. This, I hope, gives you a little bit of sense for how these birdcage coils operate and work. What's shown on the right-hand side here is just a little bit of underlying hardware. So we have these end rungs around the bottom. You have the individual rungs along the sort of sides. And those are all conductive structures, copper structures, if you will, separated by capacitors. And the capacitors tune it to be so that this birdcage coil resonates near the Larmor frequency, meaning we can put current into the system, and those currents will oscillate with frequencies that are important to us and importantly tuned to oscillate at the Larmor frequency. Now, the way this system is actually sort of powered, you're going to push a current into each of these rungs, for example, and in pushing a current, you're going to push a current into each of those rungs at a particular frequency as a function of time. And so this I0, whatever I0 is just going to oscillate as a sine function, very high frequency, right? 64 megahertz or something like this. The second term here just represents the phase. And what it means is that for every rung that we have the first current, the second current, the third current for the first, second, and third rungs. We just have a small phase delay between the different rungs. And that does something really interesting. So let's look at the current that's going through just an individual rung. This is just a wire, effectively, and it generates a B field according to the left-hand rule. And so it's going to have a magnetic field that's close to my spin system. You can think of this as being some bulk magnetization in someone's head, and their head lies inside this coil, just like what's shown on the right-hand side. This bulk magnetization, this magnetic field that's generated at this particular rung right now is going to cause a torque of the bulk magnetization. We saw before that the magnetic moments want to align with the B0 field. Well, the magnetic moments also want to align with any B field, so they also want to try to align with the B1 field. So the B1 field is able to sort of exert a torque on the underlying spins. And this particular current in this particular rung at this point in time will cause the bulk magnetization, for example, which maybe was pointing straight out of plane, to tip over just a little bit. So that bulk magnetization is supposed to be tipping slightly into the transverse plane. And if we look at what happens with the second current, again, this is just microseconds later, right? The current in this second rung is a little bit higher, and it's going to tip the magnetization over a little bit more, while the bulk magnetization is also rotating at 64 megahertz. So we're effectively chasing the bulk magnetization around by the magnitude of the current that's pulsed through each of these rungs. And then if you go to the next current, then it's going to generate even more transverse magnetization. So if I back up here a little bit, you'll see it in sequence a little bit more clearly. So just a little bit of transverse magnetization, more current from the next rung, I get more transverse magnetization, and then more transverse magnetization. And the idea is that I'm actually oscillating the current running through each of these 6 rungs at the Larmor frequency in such a way that I can efficiently tip over my bulk magnetization. And the fields that are generated in this way are also very uniform, and so the colors that are sort of shown inside this cross-sectional diagram inside the birdcage coil just indicate the magnitude of the flip angle. So if the color is very flat, it's basically green. That means we're getting effectively the same flip angle everywhere as well. Now, there's a relationship that's not easily known because it depends on the specifics of the design of the head coil itself, but those currents effectively generate B fields. It's the B fields that we care about. The B fields are what rotate the transverse magnetization. And a very simple expression for the B1 field that we generate looks something like this. We'll talk about this envelope function in just a second, but the B1 field is going to be oscillating. In this case, I'm showing it as a simple oscillation, meaning it's only oscillating back and forth along a single direction, the I hat direction. This is what we call a linearly polarized B1 field. We'll get to the circularly polarized fields in just a second. A question?
So is current flowing through each rung at a different time, right? So
yeah, I mean, every rung has like a sinusoidal current running through it. So the amplitude of the currents are just out of phase with one another.
And the frequency is of the current flowing through each rung.
The frequency, yeah. So if we go back maybe here, this is the frequency of the current that's running through it. And that frequency, I call it omega RF because it needs to be matched to the frequency. It's generating it's the underlying frequency for the radio frequency pulse. So the current that you drive generates the field, the B1 field. So those frequencies are going to be matched. And then the frequency that you want your field to generate needs to be matched to your system, which is dependent on the B0 field, the local Larmor frequency. So, okay, so what is this saying? It just says that at the end of the day, we can say that the B1 field that's generated in a system like this, we'll explain the two a little bit later, but we have some envelope function, which we'll also talk about in just a second. You could have, what I first described was actually the circularly polarized field. This field here is actually linearly polarized. You can see it's only oscillating along the left-right direction or the I direction. And I'll talk about the advantages and disadvantages of linearly polarized and circularly polarized fields in just a second. If we look at this expression just a little bit more closely, we have maybe four essential components. You have a so-called pulse envelope function, and I'll give you some examples of that in just a second, so it'll be a little bit more clear. If you just look at the right-hand side here, this is just a cosine function with an added phase. And so this envelope function here is just modulating that cosine function. So we can turn that cosine function on or off and have a rect function, or maybe we shape it with a sync pulse. And there's lots of important design considerations that are possible there. We won't talk a lot about how we design or shape these envelope functions in this particular class. If you take 229, which is next quarter, then they'll get into that a little bit more. The B1 field that's generated, we already said it, but it needs to have the excitation carrier frequency has to be matched to the spin system that you're interested in. We can adjust the phase of this thing. We'll talk about what that means a little bit later as well. And then the I hat direction just means that it's linearly polarized. And so probably importantly, and I said this a second ago, but the B1 field is perpendicular to B0. And so you can have a very strong B0 source that's polarizing your sample, but you can still have a weak B1 field that can tip those spins over because they're perpendicular to each other. They're not in opposition in any way. So here's a simple envelope function. This is just a rect function. Mathematically, rect functions are a little bit clumsy. All this means is we have an RF envelope function that allows us to turn the RF pulse on and turn the RF pulse off, which of course we do all the time. And so here you can see inside the envelope, things are precessing or oscillating, maybe at 64 megahertz or 128 megahertz or something like that. And we simply mathematically say that we can turn this pulse on at some point in time, and we can turn the pulse off at some point in time. This so-called rect function allows us to create what we call hard pulses. And these are interesting and very useful pulses in MR. What it means is, let's say you have a very uniform phantom placed inside the scanner, and you use a rect pulse to excite things. In ideal circumstances, all protons have the same resonance frequency. Your radio frequency pulse has a single resonance frequency, and you just match those two frequencies, and you can excite everything in the object of interest. And so these are oftentimes used for what we call like global excitation pulses, if you just want to excite sort of everything at the same time. We'll talk more specifically about slice selective pulses a little bit later. This is an example of one. We won't get into the details of why this is such an important pulse in MR. But the bottom line is you can still see the carrier pulse inside. It's still oscillating at the radio frequency, but it's been modulated now by a sync function. And so these become really important pulses later when you specifically want to excite a slice. The reason for that is the so-called frequency content of this RF sync pulse is such that it's band limited, so it only has a finite range of frequencies that are useful for exciting a slice, rather than doing what a hard pulse does, which is excite basically everything. Those small details aren't important right now. This is just an example of what another envelope function could look like. And in fact, there are people's careers have been built out of designing the right envelope functions for MR sequences. So there's a tremendous amount of detail and science behind specifically how these things get designed. This is the process of excitation inside the scanner. This will animate in just a second. So what we're doing right now is we're looking down the bore of the scanner, this patient. Oh, look, it is moving. Okay. Let's back this up just a second. So what we're looking at is an axial slice. So the yellow line here is just the axial slice through the patient, if you will. And we're observing the spins that are in that particular slice. And during the process of excitation, the process of excitation looks something like this. That RF pulse acts on all of those spins within that single slice. You'll notice that they're precessing, of course, at the Larmor frequency, but they're also caused to rotate over because that RF pulse exerts a torque on the underlying spins. And so we can generate so-called transverse magnetization with an RF pulse. This is in the absence of thinking about or looking at anything related to relaxation, for example. That's all right. Okay, so I want to take a little bit of time to talk about this actual sort of resonance phenomenon. And there's a little bit of a stumbling block here because we have this sort of classical understanding of things and a little bit of quantum that enters sometimes. I want to give you a little bit of insight to the quantum behind this, but I also want to describe sort of what we think, how we sort of picture this in terms of classical physics. I think I said it last time. Almost everything we need to know, and if you want to be a successful MR scientist, you can just work with the bulk magnetization, and everything works out quite well. There are some nuances that happen at the sort of the quantum level, but we'll talk about this principle of resonance, both sort of from a classical perspective and a quantum perspective. So one picture to have in mind is this. And so this is a nice, I linked to this paper on the website. This is from Dr. Hansen, and he's sort of inquiring about how much quantum we really need to know to understand MR. The movie that he's put together here is, I think, the best depiction of the state of the magnetic dipoles at equilibrium in a B0 field, right? So picture a tube of water lying in a scanner. It's got billions and billions of magnetic dipoles. And if you look at this carefully, there's slightly more in the spin-up state, say pointing this way, and slightly fewer in the spin-down state. Now, according to how he depicts it, they're not strictly in the spin-up or spin-down state because things get thermally bumped around as well. And this is where you have this hard time linking between sort of quantum and classical physics. Bottom line, you have something like this at the bulk magnetization level, meaning it's the ensemble behavior of a bunch of magnetic dipoles and that so-called Zeeman splitting phenomena that gives you a net bias in a single direction. And yet, at this point, if I put a receiver coil next to my sample, I wouldn't be able to measure anything. There's no net transverse magnetization. The only net magnetization I have at this point is strictly along the Z direction. And so this is the equilibrium magnetization when it's exposed to just the B0 field all by itself. The B1 field that we're talking about, it provides this external energy. We know it's an RF magnetic field. In quantum physics, we would say that electromagnetic radiation, which has a frequency omega RF, carries the energy that's needed to induce this transition from the spin-up to spin-down states, to go from that low energy state into that high energy state. when we think of this in terms of classical physics, we just think of the B1 field rotating in the same manner as the precessing spins. So we have to generate that circularly polarized B1 field at the Larmor frequency, and it's going to coherently, effectively push on the bulk magnetization so that we get this nutation of the magnetization into, for example, the transverse plane. If you want to look at this from an energy perspective, we know that there's an energy difference between the spin down and the spin up state, and that's related to Planck's constant, your gyromagnetic ratio, and the magnetic field that you're exposing everything to. We also know how much energy there is in a radio frequency wave, and it's related to Planck's constant and the frequency of that energy being used. And so by equivalence between putting energy into the system and the response of the underlying system, we can observe that what we need, and it's not surprising probably at this point, but what we need to initiate resonance in our system is a radio frequency pulse that's equal in frequency to something like gamma times B0, which we usually just call the Larmor frequency, or omega 0. And resonance requires that the frequency of the RF energy, omega RF, match the frequency of precession, omega 0. So if your radio frequency pulse is at a different frequency, it's not surprising it's not on resonance able to excite your spin system. And you have to be matched, right? And so you have to be within, basically a couple hundred hertz for a typical scanner to excite the water that's inside that scanner. So this is a nice picture again of the action of an RF pulse on an ensemble of spins. The blue, the sort of red and orange line is just representing the action of the B1 field on the bulk magnetization. And in this case, you can see the bulk magnetization is being actually inverted. And so if you apply that RF pulse at the appropriate magnitude for long enough, you can invert your spin system. And eventually, if you turn that RF pulse off, then the spin system will relax back to some other state. So I think this is a good picture to have in mind of what's happening to lots of magnetic dipoles as they're being acted on by an RF pulse. What we really care about and what we're going to keep track of in this course is just what's happening to the bulk magnetization vector here, which is the ensemble behavior of all these underlying magnetic dipoles. I'll make a few comments about safety, and then I think before too long we'll turn to working through some of the equations again. There's a term that comes up a lot when we talk about B1 safety. You're generating energy, radio frequency energy, and that energy is absorbed. That energy goes not just into changing the state of the spin system, but it also goes into warming up the object or the subject that's in the scanner. The measurement that's mostly used to describe this is what's called the specific absorption rate. Just a measure of the rate of energy absorption during exposure to that RF electromagnetic field. We measure in terms of watts per kilogram, so we're conscientious of how many watts we will expose a patient to, for example. And this becomes limiting, meaning that we can't just do whatever we want when it comes to MR. And in fact, one of the primary limits in MR right now is the amount is the so-called SAR limit. We can't, deposit more energy into the subject to maybe do an experiment or an imaging acquisition that we think might be interesting. In terms of when you hit that limit, it depends a little bit, but if you're doing high field imaging, so above 1.5 Tesla, 3 Tesla systems, of course, are very common here. Then if you're imaging with high flip angles, where by high I mean 45 to 90 degrees, that can be challenging, especially if your time between RF pulses is short. And by short, I mean milliseconds. So these are just sort of rough guidelines, but it's pretty easy to hit the SAR limits on any of the 3T scanners for nearly any protocol. Something we're mindful of, something that's regulated by FDA, etc., but it is something that we bump up against. The SAR itself, we can write some different proportionality relationships, and it just means that the SAR is going to increase with the Larmor frequency, and it's going to increase with the magnitude of the B1 field. So higher frequency RF pulses of larger magnitude generate more SAR or deposit more energy, and sort of by equivalence, higher B0 fields or higher flip angles are also associated with larger SAR. So we have to make changes sometimes to our flip angle in a protocol so that we come below the whatever SAR limit that we may be confronted with. big table here of just sort of what are the different guidelines. There's sort of two governing bodies, the FDA here in the US and the IEC for European countries. Something that's relatively sort of common is that we can't heat patients or shouldn't heat patients with more than 2 watts per kilogram or a body temperature increase of about half a degree. That's all considered to be benign and fine. Going above that requires operating the scanner in so-called first level mode. That means you can use MR sequences that may deposit as much as 4 watts per kilogram into the subject and can result in a body temperature increase of about a degree. And that's actually relatively common. If you look at a clinical protocol, there are probably several that require operating in first level mode. We cannot operate in second level mode unless it's a research application, and I don't know anyone here that's interested or seeking to sort of do that. People back off pretty quickly when it comes to safety and so forth. From a practical perspective, another way of looking at this is the FDA limits. This is all for whole body, meaning what's the whole body's exposure. FDA limits it to about 4 watts per kilogram over a period of about 15 minutes. So again, there's a lot of guidelines in here as to what we can and can't do and so forth. The scanners are programmed such that they limit us from entering into regimes that would result in too much patient heating. You can, though, even while operating within the limits, you can easily have people say, wow, I felt warm, at the end of your scan, at the end of that half hour, that 45 minutes. So I think the modeling community that supports industry and so forth, and the FDA, they've done a pretty good job of identifying where the limit should lie so that it's safe for everyone and yet doesn't limit performance too much for the system. We talked about this just sort of briefly, and we'll look at it mathematically in just a second. One of the expressions I showed you was for the linearly polarized field, and that meant that the B1 field was just going back and forth along, say, just the I direction. And those kinds of systems they're relatively simple, they're a little cheaper, but they also use higher RF power. And we don't want high RF power because that means there's more energy potentially going into the subject for the same effect. And so that gave rise to looking at circular polarization and how you could actually build a more energy efficient, if you will, exciting coil. And so to do that, we can generate these circularly polarized fields using a quadrature RF transmit coil, that birdcage coil I showed you before. A little bit more complicated, a little bit more expensive, but more importantly, it reduces the RF power deposition to the patient. And so in general, we always, I don't know a way of even turning it off, we're always going to use circularly polarized fields, mostly because they reduce the total energy deposition or power deposition into the patient. So what's that all about? Well, I showed you this before. I said this is a possible function for the RF pulse. You have some B1 envelope function, and it's just multiplied onto some cosine function that's oscillating at the Larmor frequency, and it's bouncing back and forth along the I hat direction. And so that's just shown here on the bottom. You have some B1 field that's oscillating back and forth along the X direction. These were common in first generation MR systems. They used this linearly polarized field because it was simple to do, and then people later figured out another option. And it's not obvious at first, but let me show you what happens. You can actually generate two circularly polarized fields if you wanted to. And we would just define the first one as being the same envelope function, and it would just be cosine on some omega minus sine on some omega. And that just means, and this is one component's along the I direction and one component's along the J direction, that just means that the total B1 field is rotating around the Z axis and is projected somewhere into the IJ plane. And this is, I think this is the clockwise field, meaning the B1 field is rotating clockwise. If you add that with another circularly polarized field, and the only difference being the sign of the sine term, that makes this a counterclockwise rotating field. And the sum of these two, if you were, we don't end up doing it this way, you'll see in a second, but if you were to add up these two circularly polarized fields, you would just recover back the same linearly polarized field. So no good reason to use two circularly polarized fields. Well, it turns out you only need, in fact, to use one of them. This first field here is on resonance, for example, because you choose it to match the Larmor frequency. And so it contributes to excitation, but it also contributes to heating. Okay? We want it to contribute to excitation. It's just the facts that it contributes to heating. This field on the right-hand side is actually rotating the other direction, right? So think about that. Your spin system is going 64 megahertz, say, clockwise, right? I should do it this way, clockwise. And now you play a circularly polarized field that's also at 64 megahertz, but going in the other direction, right? That B1 field is very off resonance, right? It doesn't have any ability to sort of excite the spin system, and so it only contributes to heating. So it's so far off resonance it can't excite the system, but it's still radio frequency energy, so it will heat the patient. That means that this second circularly polarized field is unnecessary. It doesn't help you excite, it only contributes to heating. And so the modern systems simply don't apply this counterclockwise field. We just leave it out. And the field that we actually apply is only the circularly polarized field here. So why is that so good, and why is that so useful? Well, you've decreased your B1 envelope term here by a factor of 2, right? So the magnitude of this field at any point in time is half that of the linearly polarized field. So it's the same, effectively the same excitation with half the power deposition, and that's a very useful thing in terms of being able to operate the MR system in an optimal way. Okay, so we hopefully have a little bit of a sense for how these B1 systems are put together, and mathematically what a B1 pulse looks like a little bit, and how we generate them. I want to get into a little bit more how we mathematically sort of describe some of the important parameters that we care about. So there's two sort of essential components and maybe some rules that goes with those for RF pulses. The first is that the RF pulses can be described as having a flip angle. RF fields induce left-hand rotations. B fields in general induce left-hand rotations of our spin system. That goes back to that minus sign that I talked about at the top of the hour. And by flip angle, we simply mean how far are the spins tipped over. I keep drawing my arm or using my arm as the Z magnetization, and I can tip things over to the transverse plane with a 90 pulse. I can tip things over partly with a 10-degree pulse. And the amount of tipping we call the flip angle, and we typically call that alpha as well. Now, that's not the only free parameter when we're talking about rotations. There's another one. The RF pulses can also have a phase. And that just means when I tip my magnetization, do I tip it down here along the x-axis, or do I tip it down here along the y-axis? And I can control my spin system so that I do whichever one I prefer. There may be no difference for some imaging experiments, and for others it may be really important that you tip it exactly along X and then later exactly along Y. So in principle, we need to control both the flip angle and the phase. And what I want to do is walk you through how we come up with an operator that exerts the action for a given flip angle and phase. So as engineers, you could say, oh, I need a 90-degree flip angle and I want it to be phased along the x-axis. Well, if I want it phased along the x-axis, by convention, we mean a phase of 0 degrees. If I want it phased along the y-axis, by convention, we mean a phase of 90 degrees. And so now I can say, I want my flip angle to be 45 degrees. I want my phase to be 0 degrees. What's the operator that will impart that on my spin system? So I said this a little bit already. The amount of the flip angle is just the amount of rotation that the bulk magnetization vector produces by an RF pulse with respect to the direction of the magnetic field. So that's drawn here as the alpha, and then again we can control the phase. Now, there was nothing special about the B0 field, right? The B0 field caused our system to precess. The B1 field also causes our system to precess. It's just another B field. It has a different sort of mathematical description, if you will, but it still acts on magnetic dipoles with the same physical principles, if you will. And so there is still a Larmor relationship, if you will, that tells us what's the frequency of precession, the rate at which I'm changing my angle, right, is still related to gamma, or the gyromagnetic ratio for the particular species, and the B1 field that I'm actually using. And I'll tie this together in just a second. But importantly, it's all B fields that induce precession. So we can precess at 64 megahertz because we're in a 1.5 Tesla field. It's very, very fast. Or we could use a 1 microtesla field and precess at 6 hertz. Much, much slower because it's a much, much lower magnetic field. All right, let me work through one of the first examples here. quarters. Okay, so do you guys agree or appreciate that this relationship is true? Just another B field, right? Why wouldn't it be the case? And all I want to do is show you how we go from this expression to understanding how we control the flip angle, or how we maybe choose the flip angle. And so all we want to do is integrate the left-hand side from some time 0 to the end of some RF pulse, call it tau RF. I've got some pulse, it starts at 0 and it ends at tau RF. Omega 1 might be a function of time, and I'll just integrate over it. And on the right-hand side, I'll do the same. I'm just going to integrate both sides. So same limits of integration. I still have gamma, which we know to be a constant, but B1 could, in fact, be a function of time. Okay, so in the simplest case, if B1 of time is just a constant, right? That means that we turn B1 on and then we turn B1 off. It's like using that rect envelope function. Then we know that omega 1 as a function of time is also just a constant, some other constant, doesn't matter what they are. And if that's the case, then the fact that I introduced that they could be functions of time isn't really relevant, and we just have a finite integral. And so we can say that omega 1 times time evaluated over the two limits of integration, 0 to TRF, is just equal to gamma B1 times time evaluated over the same limits of integration. Nothing too advanced here. This just means that omega 1 times tau RF, so the precessional frequency times the duration of precession, is equal to gamma B1 times tau RF. Now, if we look at this, omega 1 rather, what are the units for omega? Anyone? I hear mostly the right things being said. Something like radians per second. There is, as with all things, you got to be careful with units, right? So we typically think in terms of radians, but we don't naturally think in terms of radians. So oftentimes I'll talk in megahertz because that means more to me. But when you work things out mathematically, you got to keep track of factors of 2 pi if you want to work in terms of frequency. And then what are our units for time? They're just going to be something like seconds, right? Doesn't really matter. So the point is that the product of those two things is just radians, right? Frequency times duration just gives you some radians. We're not worried about phase wrapping at this point, which is not typically a problem with RF pulses because they're short in duration and low in amplitude. And this omega 1 TRF term, we just think of that as being the flip angle. So omega 1 TRF has units of radians, and we say, well, that is alpha. And alpha here is just the flip angle. And so in the simple case of a B1 pulse that's turned on and then off, so you can think of it this way. This is B1 T. This is time. And I have some B1 pulse at time equals 0 to time t equals tau. Turn it on, turn it off. Nothing too exciting. And all I find is that the flip angle itself depends on gamma times B1 times tau RF. And these are the two things that we actually control, right? So when it comes to designing your first RF pulse, free parameters, when it comes to designing your first RF pulse, if you know what flip angle you want here, then you just have to know what your gamma is, and gamma can change, right? You could design an RF pulse for carbon-13, no big deal. You could do it for 31p, just as hard. All you need to know is what's your product of B1 and tau RF, and then you can, of course, calculate the resultant flip angle. The longer that I turn my RF pulse on for, the more flip angle I'll get, the further my spin system will flip. The larger my B1 amplitude is, it turns out the faster it will flip, but also the further it will flip for a fixed amount of time. And these are the two things that we can control. Usually our systems have a peak B1. We can't have B1s of Teslas. Our B1s are on the order of microtesla or tens of microtesla. And we don't usually want durations that are more than hundreds of microseconds or maybe milliseconds. So these things are pretty quickly limited to a relatively narrow range of possible parameters, giving us flip angles that are useful to do MR imaging. Anywhere from a couple of degrees to 180 degrees would be common. We infrequently need to do anything to our spin system beyond a 180 degree pulse, but you could have a 1000 degree pulse. It would just mean that your bulk magnetization was going past 180 through to 360, down to 540, back up to 720, and you could keep doing that. There's nothing that stops you except for physiologic limitations of SAR and heating and things like that. But physically, you could keep it going that way. Okay, so I think that's it for that. So here's just a simple example. Say we want to design a specific flip angle. This is the B1 that I'm using. I'm turning it on, I'm turning it off. Typically, we would specify alpha. We'd say, I need a 90 degree pulse. And typically, you would want to work near something like B1 max, because that means your duration will be as short as possible. So you have a simple design problem then. You just have to figure out what's the duration of the pulse that will accommodate that. And just working through some numbers, we can see, let's say I want alpha to be a pi over 2 pulse. Pi over 2 is how many degrees? It's just 90 degrees, so that's putting all of my bulk magnetization into the transverse plane. Gamma is fixed at, there's different units you can use, but it's 4257 megahertz per Tesla, or 42.57 hertz per microtesla. We have to go from frequency back to radians, so there's a 2 pi here. And then maybe my B1 max is 60 microtesla. That's pretty high. I don't think our systems can actually do more than about half that. But all it tells you is that that particular pulse would take about 98 microseconds to play out, right? So this gives you, I hope, some sense for the duration of RF pulses, the magnitudes of the fields that we use to excite spins for maybe a given flip angle. But you can see that if your gyromagnetic ratio is changing, you'd have to change your pulse parameters. You not only have to change the carrier frequency, we'll get to that later. That was the carrier frequency was like inside that rect function, right? But you might also have to change the B1 amplitude or the duration so that you get the actual flip angle that you want. All right, let's talk about the second free parameter here. It was the phase. By convention, I usually write things this way. I put the axis of rotation along the bottom here. So in the Lauterbur book, sometimes he puts an X or a Y or, I guess an X or a Y down there. More generally, I just call it theta. So it's a little bit of a difference from the book itself. So we subscript the phase, we superscript the flip angle, and then depending on where we want to put our spins, they're going to start along the z-axis at equilibrium, and I can tip those spins down along the y-axis if I want to. That means my phase is 0 degrees, and I'm doing a left-hand rotation about the x-axis. And so that leaves my spin system along the y-axis. And if I rotate by 90 degrees with my left hand, then I go from pointing along the x-axis to pointing along the y-axis. I curl along that axis, and I take my bulk magnetization down along the minus x plane. So if that doesn't work or make sense, use your left hand this afternoon and see if you can work through some examples. A little bit more challenging is to come up with an operator. So we talked before about having a matrix operator that can act on the bulk magnetization and tell us how the magnetization is going to precess in a B0 field. We want to do the same for a B1 field. This is what I call the hard pulse approximation. I'm only asserting the flip angle and the phase. I'm not worried about the envelope function. I'm not worried about the timing parameters. I'm just saying I have an RF pulse. It has a theta. It has a flip angle. How do I come up with an operator that will impart that onto my spin, my bulk magnetization vector that I care about? The way we conceive of this is that to account for the underlying phase of the RF pulse, we just do what's called a change of basis. You'll see how this comes together in just a second. A change of basis just means we're going to rotate about the z-axis. You can see this transformation as being a rotation about the z-axis because it's just this unit vector in the far right-hand column. So we're going to rotate our perspective, our view, by theta, the phase that you've chosen for your RF pulse. We're then going to have the action of the RF pulse here as a rotation around the x-axis, so just another rotation in that new coordinate frame. And then we have to rotate back. So we rotate back by having a z rotation by minus theta rather than positive theta. And it's those three things taken in composite that give us the effect of both theta and alpha. And so if you multiply out those different rotations in the correct order of operations, so order of operations is right to left with matrix transformations, then you have the change of basis on the right-hand side here, the effect of the flip angle in the middle, and then you change back your basis on the left-hand side. What that gives you is just a relatively cumbersome matrix of sines and cosines. So I've shorthanded things here, C for cosine, S for sine, and then inserted and carefully kept track of my pluses and minuses, and you get this kind of clumsy result. No reason to memorize this. This is a really useful thing to use in something like MATLAB, and we can do exactly that. The idea is that we now have an RF operator, right? We have a matrix expression for how the RF pulse, given a phase and a flip angle, acts on our magnetization just before some event, if you will, and produces a new state of the bulk magnetization. This RF operator just tips the magnetization over by 90 degrees in a particular direction, and 8 degrees in this other direction. This code's up on the web, so you can check it out for yourselves. This just takes into, this just builds up that matrix operator for a given gamma, for a given B1 amplitude, for a given dt and a given theta. So here we're not exactly specifying the flip angle, we're specifying some of the other free parameters. We calculate the flip angle here as alpha. That comes from maybe 4 or 5 slides ago. It's just 2 pi gamma times the amplitude of the B1 field times the duration of the B1 field. We use this change of basis, rotate things, and then the change of basis comes back in here. It turns out that just the transpose of this is the same as its inverse. It's a orthogonal transformation matrix. Anyway, what you end up with here is just a little tiny operator that is the product of these 3 rotations that will act on your bulk magnetization to produce the new state of the magnetization. So just like on this previous slide, if you know what this RF operator looks like, you can just multiply it onto your bulk magnetization vector and get the new state of your bulk magnetization. Now, in principle, you can discretize this as much as you want, meaning these can be little tiny itty-bitty steps of nanoseconds, and you can just add up all of those operators to give you the final effect. Or you may choose to just have a single operator stand in for the whole RF pulse, the whole 90-degree tip. Or if you want to animate it and see specifically what's happening, you could just tip by 1 degree and then 1 degree and then 1 degree and then 1 degree. Okay. Let's take I'll take questions right now if you have questions about sort of where we stand right there. Otherwise, we'll take a short break and then we'll come back to learn more about RF pulses and then we'll get into some more work on the board. So questions? Yep.
Why do you rotate it again by negative theta?
It's just a trick of mathematics, meaning the change of basis here is just to say I need to tip by alpha, right? And in this coordinate system, I'm tipping that way. But if I had a different coordinate system, if it's just a change of basis. My flip angle only tells me how far I've moved away from the z-axis, whether I've moved this way 90 degrees or maybe I've gone this way 90 degrees. The change of basis makes sure that you're always moving along the same, call it x prime direction, and then when you're done, you rotate it back to the x direction. I can tell that's not very clear. Let me think of another way of explaining it. If I've this first change of basis here just lets me see whether my it lets me see how I'm flipping my bulk magnetization. If I was looking down the x-axis and tipping down the x-axis, I can't see that I can't measure alpha in that plane. But if I'm looking down the y-axis, then I can see it moving away from z, and I can measure alpha directly. The change of basis is just the question of whether I'm looking at my magnetization this way or I'm looking at the magnetization this way. Once I've changed my basis to see the effect of the flip angle, mathematically I still have to go back to my original coordinate system. And that just is through a rotation through minus theta. If you're not used to working with rotations, that's probably not obvious. What really, I guess, what I would say matters for this class is that you can appreciate that there is a single operator that takes into account the effects of alpha and theta at a minimum. Other questions? Yeah.
In the slide where you described the prior operator, you say the phase of 0 degrees is about the x-axis. But it appears as if in your examples, the phase of 0 degrees is about the y-axis.
Yeah. So we have to think about what B fields do, right? So think of this example here, right? If my B field is phased along, if my phase is 0, then I said that's rotating about the x-axis. So in this example here, that means my B field points along x, and it's going to rotate whatever magnetization I have that was along z is going to come down along y. So think of it, it's a left-hand rotation this way. It's curling about x. 0 degrees means the field points along x, or that the torque points along x, and it curls down along y. If I now take my hand and say my phase changes by 90 degrees, I'm pointing my thumb along y, and that's going to cause my magnetization then to tip from z down along minus x.
To go from the x to the y, don't you have to rotate 180 degrees?
To go from x to y?
Along the x.
I'm not sure if try me again.
I'm not sure of my question, but it seems as if you would have to go 180 degrees to go from to be pointing in the x direction to the y direction through the z.
Let me back up at least. The phase tells us basically where to point our thumb for the action that the B1 pulse will have on the spin system. Okay? And by designation, if nothing else, we choose 0 to be along x. And so now I have this left-hand B field that's going to torque my bulk magnetization according to that left-hand rule. And so if my thumb's along x, I'm going to take any z magnetization that I had, taking this as my initial state, and I'm going to rotate it down along the y-axis. And now if I come over to this state here, I said I'm not phased along y anymore. I'm phased by 90 degrees. 90 degrees brings me over to the y-axis, and now I rotate that way. My bulk magnetization falls along the minus x-axis. So let's say I was phased by 180 degrees. What axis does my thumb point down? Minus x. And where does my bulk magnetization end up if it's a 90? Minus y. Right? So you can work through those different examples. Those cases are easier, of course, because if you look at that transformation matrix, did I take the slide out? Oh no, I had it here. Yeah. So here's a simple case where, if you choose your phase to be 0 degrees and your flip angle is 90, then the transformation matrices become relatively simple. They're just zeros and ones and minus ones. And anytime you have zeros and 90s, that's going to be the case. Where this gets to be more interesting and harder in some sense is if you have a flip angle of 11 degrees and a phase of 45. Right? I can't do that in my head, right? But fortunately, I know how to calculate it now. And so if I gave you a problem and said, I need to phase my RF pulse along 33 degrees with a 15-degree tip angle, you could tell me where the bulk magnetization is going to end up. Other questions? All right, let's take a couple minute break and then we'll come back for another round.
There's a left and a right hand version. Yeah, different. I think it's easier to left. You do it more like you're curling around. Well, the left hand roll is just like there it is. But like, you're probably not familiar with the right hand.
So, where your fingers on your left hand end up the final position shows you where the near bolt sensation.
That's the basic.
Yeah.
That's the one where it's still no.
I mean, it's I think what's partly causing confusion, at least, is that we're used to thinking about right-hand rules and whatever, but the action of a B1 field on a magnetic dipole is left-handed,
Okay.
and so we have to work from that.
Okay.
Starting with Y.
And then your thumb is going to start.
Say that again?
I'm a little confused as to where you put your left now. Like for an arbitrary, let's say it wasn't 0 degrees at the bottom.
Yeah.
15 degrees.
Yep.
So would your thumb be 15 degrees
From X towards Y.
towards
Yeah, and so 90 gets you all the way to Y.
Okay.
Right? You could be 45 and be halfway. Whatever.
And
Yeah.
based on how far that determines. It's weird, stupid, complicated. The basics of it is it works. It has to do with rotating. There's nothing truly makes sense about it, but that's a problem with rotating frames. They're weird. Oh, you know what I think it is? It's because that's not the most
The initializer is that it's open from the organization from the X direction to the transverse.
Yeah.
Explain out the X.
Yeah. So this is the processional behavior at the longer frequency, and that's as a consequence of B0. Right. Now, if I add a B1 pulse, I'm tipping my magnetization, and the behavior is it's still precessing because it's still at B0, but it's going to tip down because of B1.
Oh, so it means still says like Z direction and just
yeah, exactly. That's why it's slowly
tipping down.
Right. So B0 is causing this precession.
Oh, so
Right.
this
B1 is doing this, but together it spirals down. So that's B0 plus B1. Yeah.
So like, this is how it actually is in physical space. Z going that way. So Z is just the same as the current going along there. And so in the same way, if you're actually seeing that arrow, it's not a Z direction. So that's just showing you what's not around there. And so it's set up so that once this falls down there, you'll notice, and it's the point in time, this comes the direction of the field. That's all doing with the phase to make sure that your fault magnetization does not actually get like, once it gets knocked in the transverse, it's not getting bounced around or whatever. Magnetic fields you have.
是让它的磁场给贴降下来。那么这两个作用的效果。
I mean, I understand this to a degree, but it's like I can't properly explain this.
No, I understand. Just the flip angle is nice.
I understand this at an incredibly basic level. I somehow, my mind knows it's right. I don't know how to properly explain it.
Okay, I love that there's discussion, but I also feel that there's some confusion, right? So hit me with a question or two. What I'm gonna do is I want to talk about this for a second more because conceptually I want it to sink in. Then there's maybe 10 slides on types of RF pulses that are not terribly exciting. You can just read them on your own. And that'll let me jump ahead a little bit and we can do the stuff that I really want to do, which is work on the board with you guys about some of the other processional behavior that we can observe that may or may not clarify some of the stumbling points right now. But ask me a question or two about points of confusion on the action of RF pulses or the description that I've given for how RF pulses act on the bulk magnetization. Or just say do it again. I don't know. Clear as mud, right? So what was I heard some discussion. I heard just right hand rule, left hand rule. Unclear about why my thumb points this way and which thumb do I use, right? So probably part of the confusion, you're not used to thinking about sort of left hand rule. That just arises, if you go back to the very, very first slides that I brought in today, it was all about this minus sign, right? This is just the physical action that the B1 field has on the bulk magnetization, right? If we'd chosen to define our gyromagnetic ratios as they're negative, then there wouldn't be a negative sign, but physically we can't escape the fact that when we apply a B1 field, it does something to a magnetic dipole, and it happens to go according to the left-hand rule and not according to the right-hand rule, okay? That doesn't say, I haven't changed the physics of the B1 field that's being generated. I'm just telling you which way the bulk magnetization is going to rotate if I generate a B1 field or any B field, okay? So that we have to accept as empirical from physics. And now I'm trying to lay the groundwork for the mathematical description of what's known to happen and do it through a matrix description. And so if we go back to, yeah, this one's fine. Yeah. So in this example here, we said this is an RF pulse whose phase is 0 degrees. By convention, that means think about a B1 field that's oriented along the x-axis, meaning you can think of it as the current running down my x-axis, and I'm going to generate this left-handed field, if you will, through the x-axis. If I go to 15 degrees, I'm going to rotate away from x towards y, and then through 45, 60, and eventually 90 degrees. Then 90 degrees will have my thumb pointing along the y-axis. If my thumb points along x like this, then the effect on this magnetic dipole that was at equilibrium, or the bulk magnetization that was at equilibrium, is such that it's going to tip down and point along the y direction. I see a couple more nods. The second example that's here is saying, well, let's not phase it about the x-axis, let's phase it about the y-axis. So I've rotated my B1 field to point along my y-axis here, and now I tip over my bulk magnetization that was pointing straight up, and when I do that, it now points along minus x. So let's say my phase was 270. Where does my thumb point? Minus y, right? 0, 90, 180, 270, right? So let's say it's 270 for my phase and 90 degrees for my flip angle. Where does my bulk magnetization land? Plus x. So we got a few more plus x's out of that answer than we did with the first plus y. Yes?
So in the slide that which you abbreviate the cosine and sine as CNS, can we just use that matrix and plug it into math?
Yes. And that's all this does. This is, rather than sort of writing out that longer matrix form that has the sines and cosines and sine squareds and cosine squareds, this just uses that change of basis operation, exerts the appropriate flip angle, and then effectively rotates back so that it has the same effect of that operation. So this function here just behaves ultimately just behaves like this. Okay. Now, if what you wanted to do, let's say you wanted to, you've seen a lot of movies. All the movies that I'm generating here, it's all done in MATLAB, and it's all done using this operator, right? And so if I want to generate a movie of my bulk magnetization doing this, I just have to, in this example, I have to choose a phase that's something like theta. This is probably drawn wrong, I'm realizing. Let's just say that we choose a phase so we can tip our magnetization. This is the operator that will let me do that. If I want to, I can just have a small amount of alpha for a given theta. I could just have a small amount of alpha and tip it 1 degree, and then I could operate on my bulk magnetization with that same operator and tip it 1 more degree, and multiply it again and tip by a degree, and tip by 2 degrees and 3 degrees, and build up all of those states of a total effect of 90 degrees. And that way I would see the bulk magnetization moving through those different states from its equilibrium position to its fully excited position. Yep.
So we just have a B0 and we're just precessing around the Z-axis.
Yep.
And then we introduce the B1 and it starts to... Does all it do is change the angle of the precession?
Kind of, right? So it's a great question, and we're going to look at this mathematically in just a second, but it's a nice lead into what I want to do next. So if we jump to, let me just show you this. I showed you this earlier, I think. Hopefully it's this one. Yeah. So this is a question during the break as well. This is just showing so-called forced precession in the laboratory frame. Okay. So what are the requirements for forced precession? What B fields exist? What B fields are turned on? B0 and B1, right? So B1 is what's giving me that sort of obvious precessional behavior of causing it to rotate. But while I have my B0 field on, my B0 field's always on, and now I put RF energy into this system, and I can't do it very well with my arm, right? But eventually it lies flat along some particular direction, given the RF pulse is on for long enough at the right frequency for the right amplitude.
So what determines its natural angle of precession?
The equilibrium state is just here, right? So if you just put a bucket of water in the scanner, the bulk magnetization is just going to point along Z, and it's just sort of like, you can't quite see it, right? Because it's just precessing along its own axis, right? It's not until it's off axis that this wobbling behavior becomes apparent, right? And then when it's way off axis, then you can totally see it. So importantly, this is forced precession in the laboratory frame, and what you end up with is this sort of spiral, right? The spiral as the magnetization eventually goes to lie flat. And I'm going to show you, I think it's the next thing I want to do actually, is show you how mathematically we would get there, and then we'll sort of be confronted with a set of equations where we go, that's a little harder to solve, and we won't solve it, and then I'll show you the advantage of instead switching from the lab frame into the rotating frame, where this behavior of this precession is basically taken out. It's called demodulated. We take away that precessional behavior, and then all we see in that rotating frame is just the magnetization tipping down. And I don't have to wiggle my hands doing the precessional thing.
What's the reason all for 3x3 matrices 4x4 math?
Yeah, it's a good question, and I mentioned it only briefly in the previous lecture. When we add the concept of relaxation, this 4x4 transformation will turn out to be important. Right now, it's just a placeholder, but for consistency for things later, it's helpful to form it that way. It's basically a placeholder for a term that we need later, but it has no effect. It's a good point. If you look at the code, just back here, just quickly, Knauf, right? Yeah. What Knauf is picking up on is that I've written this out as a 4x4 matrix. That actually means that your bulk magnetization vector has to be a 4-element vector. And so it's the mx, my, mz, and then just a 1. Again, you'll see why that's important when we talk about relaxation maybe Monday. But for now, you have to multiply it by a 4x1 element matrix so that it was consistent in terms of its dimensionality. And then you'll have this fourth term that's kind of irrelevant, and you basically just ignore it. Again, you'll see why we need that later, but it's helpful to keep these things sort of in the same formulation, if you will. Okay? Okay, so there's this section on types of RF pulses. I'm watching the clock here a little bit. I'm going to skip past this. It's easily read, nothing terribly exciting, and we'll come back to some of these concepts as we actually need them for some of the pulse sequences later. So I want to talk about these special cases again. So at the end of the last lecture, we had worked our way through free precession in the laboratory frame and got this result that just showed us that the transverse components of magnetization precess. They have these sine and cosine terms. And the Z magnetization in the absence of relaxation doesn't do anything, so it's kind of uninteresting. What I want to work through, we'll see how far we can get. I'd like to work through all three of these today. We may not get through the fourth one. So what we'll look at is force precession in the laboratory frame, which is what I just showed you, the sort of spiraling down of the bulk magnetization. I'll show you what that ends up looking like. It's a little bit complicated, and it gives us the excuse to begin working in the so-called rotating frame. So force precession in the laboratory frame, again, we're not worried about relaxation yet. I won't work on the board for this one because I just want to work through it a couple steps so you can see what it would end up looking like. The idea is that we have the equation of motion, but our B field now has been compounded. We have not just B0, which was all we used last time, but we have B0 plus B1. It's just a B field, we just have to add it in and account for it. When we look at taking the cross product of these two terms, you'll remember we write our unit vectors across the top. We write our magnetization, bulk magnetization vector components along the middle, and then we just spread out our B field across the bottom. Our B0 field only has a K direction, so it only ends up in this far right-hand term, if you will. And our B1 field only has I and J components to it, right? It was this B1 envelope function plus an I hat term and a J hat term. And so we just put the I hat term here in the I hat column and the J hat term here in the J hat column. And now we have to carry out the determinant operator to figure out what's happening to each of our components of magnetization. And we get something like this. So remember, this time rate of change in the bulk magnetization vector is really three different time derivatives. It's telling us what happens to mx, what happens to my, and what happens to mz. If we look at our determinant up here, I have the I hat direction. I have to multiply my on gamma b0. That gives me my first term here. And then it's minus something like gamma b1 envelope function of time times mz. And that gives me this second function here. Is this determinant operator familiar for everyone? Okay. And so all I've done is written out what these individual differential expressions will end up looking like. And the main point is you have some pretty complex coupling now. It's not that we can't write down a solution to this, it's just that we're too tired. So if you look at the dmx dt term here, it depends on my and mz, so that kind of stinks, right? The my time rate of change term here, it depends on mx and mz, and the mz term here depends on mx and my, right? So there's pretty complex coupling, so to speak, between these terms. It's not so bad. We can solve it. We know what the solution sort of looks like. We can kind of guess at forms that are going to work, but needless to say, it takes a little bit more work to sort it out. We know what our B1 field looks like in actuality, meaning it's some envelope function, it has some I hat component, some J hat component. And so again, we can start being a little bit more specific about what these equations would look like, but that doesn't really help things much. You still have coupling. Mx depends on my and mz, my depends on mx and mz. It's a bit of a mess. And so I don't want to really work through how we would actually solve that. We know what the solution looks like. We looked at this just a second ago. It would have to describe this combination of precessional behavior from B0 as well as precessional behavior from B1. Now, because B0 and B1 are totally different in terms of orders of magnitude, right? You'll see that the B0 precession, it's circled around in the transverse plane many, many, many times, maybe 10 times or whatever, but it only slowly tipped down into the transverse plane. That tipping into the transverse plane is only a quarter of a revolution, right? The B1 field is much, much, much smaller than the B0 field. And so in the actual physics of these systems, we're going to precess around, at megahertz frequencies, but we're only going to precess into the transverse plane at much lower frequencies. So precessing down in the sort of like kilohertz range, and precessing around in the megahertz range. So big orders of magnitude difference there. Okay, so force precession in the laboratory frame, a little bit complicated. Mathematics is a little bit confusing and coupled. but that's okay because there is a simpler way to describe these things, and that's to transform everything from the lab frame to the rotating frame. So what I'm going to do, there's a lot of this in the Lauterbur book. I'll probably, I used to do this derivation in class, but it's one that I've taken out as well because it's a lot of just like, a lot of substitutions and carrying over terms and algebra and this kind of stuff. And it's, while it gives you some insight as to how to do this mathematically, I think we can jump to the physical insight without slogging through the whole derivation. I'll see. Maybe I'll still put that up online so you guys can see the steps that we go through. But I'll talk you through some parts of it so you maybe appreciate where it sort of comes from. The bottom line is that working in the so-called rotating frame simplifies the mathematics and I think permits a more intuitive understanding of what's going on. So on the left-hand side, this is what's happening, right? If we were to stand by the scanner and sort of observe our bulk magnetization, it would be doing things like this. But mathematically, we only want to think about it in terms of what effect does it have on putting magnetization into the transverse plane. And so when we demodulate or mathematically get rid of this precessional behavior, the only thing we observe is the bulk magnetization tipping down into the transverse plane. The state is still the same. It still ends up with magnetization fully in the transverse plane. It's just mathematically a lot easier and conceptually easier to visualize that magnetization is doing what's happening in the rotating frame as opposed to what's happening in the lab frame. So here's just another example. Which coordinate frame am I actually talking about here? I'm showing you an RF pulse as a function of time, and I'm showing you what happens to the Z component, and I'm showing you what happens to the X and Y components as a function of time. I think this is playing. There you go. So what coordinate frame am I showing you this? What perspective do we have? You can either pick it up from this information or from this information. Yeah, that's all lab frame, right? We still see very apparently the precessional behavior of this system, right? What was the flip angle? My magnetization starts in this state. I hit it with an RF pulse. Hopefully, there it goes. So you see it wobbling around, and then the RF pulse really kind of takes over and tips it down. What's the flip angle? 90. Just 90. Yep. Okay, so we saw this before. I didn't actually show you this exact figure of how we define the coordinate system for the MR scanner. I really should have drawn the origin here at isocenter, which would be sort of positioned in the middle of the B1 coil, if you will. But we generally take the Z-axis as the head-foot direction, X-axis as being left-right, and the Y-axis as being anterior-posterior. And we know that the rotational angular velocity just depends on the B0 field that we're using, and then the gyromagnetic ratio of the species of interest. And you know, the laboratory coordinate system is useful and everything, but we really want to make this transition over to the rotating frame. So how do we do that? Let me see. Oh yeah, I really knocked the whole derivation out. Lucky you. Okay, what it ends up looking like, you have to go through a lot of transformations to be able to do this. And the idea is that we know what the I hat and J hat direction is in the lab frame, and then we can define an I hat prime and a J hat prime direction in this rotating frame. And so we kind of expect that the relationship between the two is something like a rotation at the Larmor frequency. We're just effectively getting into the spin system and precessing at the Larmor frequency with the spin system. What that ends up resulting in mathematically is that the bulk magnetization in the so-called rotating frame. So today we're going to subscript things as sub-rot. Eventually we're going to even drop that subscript and just assume we are in the rotating frame. And this equation of motion looks a lot like what we had before. So it's still the time rate of change of the bulk magnetization in the rotating frame. It's equal to the bulk magnetization in the rotating frame. The only thing that's really changed is what's on the right-hand side of this cross product. Still depends on gamma. And now we have two terms here. Before we just had the B field, and that was the B field in the laboratory frame. Now we have a B field in the rotating frame, and we also have this so-called fictitious field, okay? It's a lot of mathematics to introduce this term here. This term here just offsets, it effectively cancels out, if you will, the effects of the B0 precessional behavior. It just lets us demodulate or get rid of that precessional behavior from B0 alone, and then we can still keep track of everything else. We can write this last expression here, which is the kind of the compact form of the equation of motion that looks a lot like where we ended in the previous lecture. And here we just introduce the so-called B effective. The B effective field is just the effective B field that the bulk magnetization experiences in the rotating frame. Okay? That means it's the sum of this so-called fictitious field, this thing we have to add in there to get rid of the effects of the B0 field. And I'll show you how that looks in just a second. The B rotational field may be as simple as just the B0 field, right? That would be the simplest case. We want to describe the bulk magnetization dynamics in the presence of only B0, then this is going to reduce down to something very simple, which I'll show you in just a second. So the bottom line is we have some different subscripts, but the equation mathematically still looks very similar to the equation of motion that we had in the lab frame. And the only trick here is we're introducing this so-called fictitious field, which effectively negates or offsets or demodulates the presence of our main B0 field. Because this term here should look a lot like the conventional B0 term, just from the Larmor expression. Okay, so let's see how we actually go about doing this, or let's work through an example of doing it. Okay, so this is just the example of free precession. This is going to be in the rotating frame. And of course, we're not really worried about relaxation yet. We'll bring that in on, I think it's Monday. Okay, so what's the B0 field if we're just talking about free precession? We have our B vector field. We have to describe it so we can put it into our new rotating frame expression. If we're not working in the rotating frame, what's our conventional externally applied field? How do we write it out? Now, this is just free precession, right? Yeah, B0 what? B0 K hat. B0 pointing along the K direction, right? Well, in the rotating frame, is it any different? I heard a no. It's not, right? We still have the same magnitude field. It's still B0. It points, you could say, along a different direction, just the K prime direction. But in the laboratory frame and the rotating frame, they share the K direction, right? Everything's precessing about Z. Nothing has changed in terms of components along the Z-axis. And so in that so-called rotating frame, it's just the same B field. So in the case of free precession, that's all we're talking about right now. In the case of free precession, the B field in the lab frame and the B field in the rotating frame are all the same. Slightly different ways of writing the same thing. So what's our B effective then? We have this B effective field. We defined it just a second ago. We skipped a bunch of the mathematics that get us there, but it depends on omega rot by gamma plus B rot. Easy enough. We know that omega rot by gamma, I guess I should write, we know that omega rot by gamma, I could write it here, omega rot is just equal to gamma B rot. And so omega rot divided by gamma just equals B rot. There should be a minus sign in here. Sorry. Oh, right. There's my minus sign on this expression, right? And so then just by making those substitutions, I just have something like minus b rho along the k at prime direction plus b rho. I should write it. That's fine. We can get rid of that. So in the in the rotating frame under the conditions of free precession, meaning the only externally applied field is the B0 field, the so-called fictitious field perfectly offsets the underlying effect of the underlying B0 field that we apply. So under these conditions, there's no B effective. Right? We just showed that it's basically equal to 0 for specifically, you could say, for on-resonance spins. And more importantly, in the absence of other B fields. So we don't get a really interesting result out of this other than we're showing mathematically that when we introduce the externally applied B0 field in the rotating frame, the effective field is 0. Why does that matter? How's that sort of interesting? Well, we can carry this a little further and look at the actual equation of motion. So dm rho by dt was just m rho crossed with gamma times this B effective field which we just showed was equal to 0. Right? And so that means that the time rate of change of all components in the rotating frame is just 0. It's just the 0 vector. So by inference, we know that if the time rate of change is 0, then the components of the bulk magnetization as a function of time are just equal to some constant. And so that means they're effectively stationary in the rotating frame. So not an especially interesting result, but hopefully one that makes sense to us now. Meaning, if we want to describe free precession in the rotating frame, there's nothing to observe. There is no precession anymore because we've effectively demodulated it with the introduction of that so-called fictitious field. Questions about that? Okay, so I think the next example, yeah, I'll just move to the next. This will get a little bit more interesting. We'll see how far through this one we get. We'll get partway. Okay, so that was the not terribly interesting result of looking at free precession in the rotating frame. Now let's go look at forced precession. This is where things pick up a little bit. So forced precession in the rotating frame without relaxation. So the first thing we need to do, we need to procedurally go through a couple different steps. The first one is let's define our B1 of t in the rotating frame. We know what the description is in the lab frame. We talked about that at the beginning of the lecture, kind of middle of the lecture. After we do that, we want to define the B effective field. In the rotating frame. So we have to do these sort of coordinate transformations, and I won't go through sort of every little step there, but I'll give you the sense for how we go about doing that. And then the last thing we're going to do, this is sort of just the outline of the steps. The last thing we're going to do is define the equation of motion for the case of force precession in the rotating frame. So we'll end up with that system of equations that we can work through, either the sort of closed form solutions, and then we can be specific about the actual B1 field that we apply. So earlier on in this lecture, we gave a description, this is of my B1 field itself. So my B1 field as a function of time depended on some B1 envelope function. That was the thing that could be that rect function or sinc function or many other things, as it turns out. And that was just operating on top of a cosine and a sine term. The cosine had to have radio frequency energy at the RF frequency of interest times time, and we could, in theory, add some phase to that, and that would oscillate back and forth along the I direction. And then we also had a sine term. So that was just the definition of a possible B1 field that we would use, a circularly polarized B1 field. We'll do a couple simplifications. Let's not worry about theta. We'll just let the phase be 0 so we don't have to carry it around all the time. The thing we need to do is this first task. We need to define B1 of t, our B1 field, but in terms of the rotating frame. And this coordinate system here and this coordinate system here, those are lab frame coordinates. So what's the relationship between the two? We know that I hat, it's defined as being cosine omega, say RF of t along the I hat prime direction. I'll explain this in a second. Plus sine omega RF times time in the j hat prime direction. So if we take our axes, our lab frame axes to be the I hat axis and the j hat axis, then we're just defining a transformation to the j hat prime and the I hat prime axes. And the rotation of this system here is happening at a frequency omega RF. So the relationship between those two coordinate systems, here we can see the rotating frame. And its relationship to the I component of the laboratory frame. We need to do the same thing for the j direction. These are just sort of by definition. So we'll define the j direction. And it looks a lot like those other rotation matrices. If you can't tell yet, I really like rotations. So if you look at the sort of the sines and cosine terms inside of here, this is just another rotation about another axis. And again, you can see those rotating frame directions popping up again. So all I'm going to do is just substitute these into the first expression we had for B1 of t. Okay. Not too exciting. It's always nice when you work with sines and cosines, right? Because things always cancel. So if we put those terms inside, then we'll end up with our leading B1 envelope function, which can be a function of time. we have something like cosine times omega RF. And now I need to multiply that by my I hat direction in the components in the rotating frame. So that just looks like cosine omega RF times I hat prime plus sine omega RF times time j hat prime. Close it off with the parentheses. And then I have a minus sine term operating on omega RF. And I need to bring in my j, my description of the coordinate axes in the rotating frame for the j direction. And that just looks like minus sine omega RF times time I hat prime. And I'll squeeze it in, plus cosine omega RF times time j hat prime. If you missed that, this is just the I hat direction. This is just the j hat substitution. I'm just going to collapse some terms and show that the B1 envelope function as a function of time now just operates on, if you carry out the multiplication of terms, you'll see, no surprise, perhaps, that you get a cosine squared omega RF times time term along the I hat prime direction, plus a sine squared omega RF times time along the j hat prime direction. There's some other terms that cancel out, some sine times cosine terms that cancel out, so we won't worry about those. We know the identity of cosine squared plus sine squared equals 1. And so we just end up with our B1 envelope function as a function of time along the I hat prime direction. And so what does that mean? Well, that just means that in the rotating frame, oh, I'm sorry, earlier on here, I should have shown you that this was in the rotating frame, because it's important that the whole point of this was to define B1 rot. All right. And so the whole point is to say that in the rotating frame, the perception or the way we see the action of the B1 pulse is much simpler, and it's just this pushing down along a single direction. There's no sines, there's no cosines, and that links back to that movie that I showed you, the magnetization just tipping straight down. It's not precessing around in some crazy way at the same time, it's just pushing down along a single direction. We kept it simple by getting rid of the phase. We could make it more complicated by adding the phase, so we could tip in any direction according to the phase, but we didn't do that now. Question?
Is this sine squared I direction?
Which term, sorry?
The second term, cosine sine squared.
Here?
Your second to last line.
Here?
Looks like a J, not an I, next to the sine squared.
You're right. Yep, sorry. Thank you. That's an I hat prime. Otherwise, we have a problem. I just want to write I's and J's together, right? So, got out of sync. Okay, are we okay with this page? Yeah? Almost, not quite. Let me make a move. Almost. I'll try to get through, I guess, this next page. It goes kind of quickly, and then we'll call it a day. Okay? It's all recorded. I shouldn't say that, right? My worst fear is you guys will stop paying attention and stop writing things down. I'll have no reason to get up in the morning. Be depressed. My research will go downhill. Okay. So just continue with this. We defined our B1 envelope function now, the actual RF pulse. Let's go back to the equation of motion in the rotating frame, because we now want to use that actual B1 field. And so we know what that looks like. You guys can maybe hopefully almost write it as quickly as I can. So that is just the equation of motion in the rotating frame. We now know the B effective that we want to talk about in this case. So we have M rot crossed with gamma times V1 envelope of T along the I hat prime direction. If we carry out the cross product again, we'll see what kind of system of equations we end up with. So we know we have I hat, J hat, these should be primes, I guess. J hat prime, K hat prime. The components of our M vector are just something like, I should write it as MX rot, MY rot, and Z rot. And now the B field that we've chosen is a relatively simple one in this case, right? Because we effectively got rid of anything that would have been the B0 term, and we only have a B1 field pushing along a single direction, the I hat prime direction. And so we just carry that field down into the first position, gamma B1 E of T. How much effective B field do I have along the J hat prime direction? 0. And how much do I have along the K hat prime direction? 0. So this is linking back to what I said sort of towards the beginning of the lecture. The solution here looks a lot like what we had before. The form of this determinant looks a lot like what we had before. Now we have the B1 field in the X position, if you will, whereas previously we had the B0 field in the Z position. So the solution to this isn't going to perhaps surprise you too much. This looks already a lot like free precession in the lab frame. We can write out the actual individual expressions if you want. So I'll call this dmx prime. It's just a little bit shorter hand, times dt is equal to 0. So the cross product along the I hat prime direction just gives me my rot times 0 and mz rot times 0. If I write my dmy prime dt term, that's just gamma B1 effective times T along the times the MZ prime. I should have, I don't know why I didn't do it here. I'll just call these primes. And then the last thing we need to write is what happens to our Z magnetization. So MZ prime dt. And that just comes out of the last multiplication here, but you have a minus sign from the cross product determinant term. And that's minus gamma B1E of T M Y. So not surprisingly, we end up again with a coupled first order ODE. And we mostly know how to solve that. We know what we did last time. Last time we said, oh, we've got some differential equations. They're coupled. You need to differentiate both sides, and then we can do some substitutions and isolate some terms and get something that looks just like a second order differential equation, but not coupled. And we felt like we knew how to solve that a little bit more easily and more quickly, and so that was in fact what we did. Yeah, given the time, I'll go ahead and wrap it there. What we'll do when we come back, it'll probably be one of the first things that we do. We'll work through a specific solution to this expression here, where the interesting thing now is that this B1E of t term and this B1E of t term, of course, the same thing. Those are now functions of time, so we can't just throw in a constant exactly when we look at the solution, but we'll work towards a solution that tells us the whole goal, right? What's going to be the goal at the beginning of the next lecture is what's mx prime as a function of time? What's my prime as a function of time? Oops. And what's mz prime as a function of time? Can anyone answer the first one for me? What's mx prime as a function of time? Perfect. All right, so we're 1/3 of the way done. All right, guys, have a good weekend. If you have questions, come grab me. Otherwise, I'll see you Monday.